Okay, so what we have been doing so far is investigating and developing a language for proving mathematical theorems. And the main objective for you guys was to investigate a bunch of so-called logical laws or things like that, and actually start appreciating some subtle or not so subtle differences between things that most mathematicians would consider tautologies, such as things like, I think, sorry, I'm getting confused by my tools here, such as the law of excluded middle, which I conveniently excluded from your homework list. But you had a similar one, like it was a law of double negation, and we were trying to investigate to check whether it makes sense that we have an equivalence between the proposition P and the proposition not P. And it's important to appreciate that the law doesn't state that my favorite proposition P has this property. It's like every mathematical proposition has this property. So when we say the law of double negation, there is an implicit for each proposition P here, this is valid, or I could write it like that. Now that we are more familiar with this symbol, from P I can prove the double negation of P, and from the double negation of P I can prove P. And similarly, the law of excluded middle has the same thing here for each proposition P. The following is provable or true, whatever you want to call it now, P or not P. So you were not assigned anything about this, but you were assigned something about this, and you actually solved it. And we can talk a bit about this. So the idea here was, let's go through the proof. Okay, so which of the two is provable here? You're only three, so yes, please, Arati, go on. From left to right. Yes, so how does this proof go? I want to prove from P. Okay, if I actually start like this, the first step is to suppose P. Of course, I don't have much choice here. And now what happens is that from P, I want to prove the double negation of P. And now I can remember that what this actually means. This means that not P implies boom, implies this contradiction, and so I know how to attack this implication. I just need to suppose the left-hand side, suppose not P, and now my goal is to reach a contradiction, but I have P and I have not P, and therefore I can do it very easily, because remember, not P is just P implies boom, which means that I have P. So I have this implication and I want to use it, and the only way to use an implication is to manage to get my hands on a P, and I have a P already on my inventory, so I can use this on this to get this, which is exactly my goal, and therefore I can say something like apply not P, we'll do it directly on P, and from this I got the contradiction I wanted. Small detail, it doesn't matter much here, but technically I have two ways to finish this proof off. Can somebody see them? Like the last step, I could do something else. What is my state here on the third line? I have P. I have not P. I have a contradiction, and what I want to prove is a contradiction. Yes, Arati. Γράψουμε τι? Double negation of what? Like this? But with what kind of command? So my question is, I'm here, I haven't finished off, and we've already seen that I can use make use of the fact that I have this special guy on my givens. So I can explode the wall, and this is one way I can finish it. It's done. But like my question is, what else I could do here? Instead of exploding, using the bottom to explode the world, there's something else I could do? Yes, Konstantinos?
Επειδή έχουμε και το P και το άρνηση P, θεωρητικά είναι σύζευξη, οπότε πάλι καταλήγουμε όμως εδώ.
This is pretty much the same thing, because what you're saying is we have this, we have this, these two guys here, and therefore I can combine them to get this and explore the world and prove whatever I want. So the technical thing, that it doesn't matter much, but the idea is either I use this to explore the world, or I say I got my goal on my givens. So I could finish this off like, I don't remember what the word we used, I think it was exactly or immediate or something like that. Exactly, because I already have my goal. I have bottom on my givens, so that doesn't make sense. It's like if I had my goal was G and I manage G on my givens, I can already finish my proof. I have my goal on my givens, and now I do have my goal on my givens, so I can either say I'm done, I have my goal on my givens, or I can not even look at my goal and say I got the atomic bomb on my givens, I exploded and I'm done. Okay, yes.
Άρα το bomb δεν κοιτάει καν τον goal.
It's my choice. If I decide to use it, it explodes everything, it doesn't care about the goal. If I decide to say, this is my goal, I'm done, I didn't even use it, technically. It's more or less, let's say you have a conjunction, and a different example might make my point a bit clearer. If you want to do this, one way to do it would be like, I already have my goal and my givens, I'm done. Because it's exactly the same thing. Mind you, this would not work if this was like that. Q and P. This needs a proof, right? But technically, one way to finish a proof is observe that among your givens, you have exactly the same thing as your goal. So you are done. You don't need to do more stuff. Yes, Areti?
Το πρώτο είναι το άτομο και τώρα αυτό είναι ότι πήγα τα...
Okay, you said atopo, which would translate to like a reduction to the absurd, something like this. And so the first one is not exactly this. It's like a use of the contradiction. And you could write something like contradiction here. It's a synonym for boom. I have arrived to a contradiction. You could call this a proof by contradiction. I'm just trying to be careful here to differentiate what happens here, which is completely valid constructively, because we have like bottom and we're using it, and that's it. That's the only way we have to use bottom. Versus what happens sometimes when we're starting to prove something and we assume the negation of it and we arrive in a contradiction. So these are the two things that are completely different. And I think, especially, I think it was Areti who proved this, and we should already start to appreciate that these things are not the same, and therefore, if a proof proves this, if a proof proves this, we don't get the right to say that we have proven this. So essentially, this reduction to the absurd, the satopapagoghi, is kind of like, it's not being honest, because you were asked to prove P. If you see what you actually proved, you proved the double negation of P, but you don't bother about it and you say, okay, therefore I accept this as a proof of P. So pretty much this whole idea is, let's be honest, okay? So does that make sense, this proof? I hope it does. We've seen it in Zulip. So rapidly, I'll try to prove the converse and see where the problem lies. So, okay, let's say we start off like that. Double negation of P implies P. So the first obvious thing to do is suppose the double negation of P, and now I have it, and I want to prove P. And okay, if I'm a pessimist, maybe I can already realize that there's not much point in going further, but let's say I'm an optimist, and I want to try my luck with the only thing I can try, which would be, remember that this is actually an implication, so there is hope. Because I have something, I haven't used it, and the hint my mother told me is like, the answer is on your data, on your givens. Use them if you haven't especially. So it's like, I just put all my hopes in finding a way to use this. And the only way to use an implication is if you manage to get its left-hand side. So I say, okay, I'll try my luck. I'm claiming that I will be able to prove the left-hand side. Be careful with this claim, like syntactic sugar or what you want to call it, because this doesn't give you anything for free. You are just arguing that with the givens that I already have, I think I can manage another given that I would like. So if I get to prove it, I have the right to claim it in my givens. So here opens a sub-proof in which I need to prove what I'm claiming that I will prove. So my goal is this, and I obviously have no right to get more givens for free. The idea is that I'm claiming I can get this from my current givens. So this will be like not P here, and my givens are not P. And I can like pretend that I'm happy a bit because on my goal there is an implication. So I say, aha, I can do one more line, at least one more line. What's the next line I can do here? Someone, please. Okay, so just to help, just a second, I'll remind you what my goal is. My goal is P implies boom. So there is at least one step I can do further here. Okay, let's pretend that I managed to finish this off. Why am I happy? In this case, I'm happy because the moment I go back to my original proof, I'm gaining this guy as a given. And then I can finish this thing off. Because I already had this guy. Sorry. It's a mess. And my objective was what here? It was P, right? Somebody help me? Yeah, it was this thing. So my goal was P. I opened the subproof here, so everything goes back the way it was, with the only exception that I gained the thing that I claimed that I was going to prove. So the idea is that I claimed this, so I gained this here, and nothing else changes. So how can I finish my proof now? Yes, Arati? Oh yeah, you're answering, yes, the previous question. So here I would indeed suppose P. Where is it here? Suppose P. And okay, let's ignore this a bit and let's go back to the supposed future where we managed to prove this. What would I do here to finish my main proof? Yes, Sarati again. Perfect. You apply which on which? Like, let's see.
Not bad.
Actually, it's the other way around, right? Because this thing is like the function you're applying. Remember, this thing is like not P implies boom. So you apply this guy on this guy and you get this guy. So this is like apply not P on P. And from this you got a boom, right? Okay. Let's say that we have matured a bit and we don't want to, every time that we manage like a proposition, I don't know, a proposition Q and its negation somewhere on our givens, we should be able to just say contradiction and be done with it. I hope you are happy with this. But like, pay attention that I'm not expanding the things I can prove. I'm just saying, okay, give me a break. If I have something in its negation and I write contradiction, please understand that I'm actually applying this on this. I'm getting a boom here, a contradiction here, and then I'm exploding the word. I don't want to keep writing all these bureaucratic things every time. So from now on, I will start using like this abbreviation. If I say contradiction, I'm implying that you have something in this negation already in a givens, and it is a pretty trivial thing to check. I mean, I shouldn't be forced to show you it's here and there. It's a simple thing. Loop over it and you'll find it. Okay, so actually, did we prove this? No, because we haven't finished this part yet. So crucially, the whole proof depends on this thing. And if we can finish this, we are done. Okay, so Areti gave the first line, which is correct. And what happens here? What is our substate? Be careful, there is a new scope within this part. So changes like this change that happened within here will not affect anything the moment we go out of the scope. So let's let's try to prove this a bit. Okay, I don't know where I should write this. Let me get the whole thing. Let me try to move the whole thing on the new page. Okay. So crucially, our proof depends on finishing this thing. Okay, but okay, humor me. What can we do? What's the goal here? After this line, I have not P. I have P, and I need to prove somebody. This was actually here, right? Okay. So what am I trying to prove? Yes?
So one is P.
Not P. No, it just changed with this command. Remember that supposing something changes both the givens and the goal, Lazarus? Boom, yes, the bottom. It was okay. Maybe I should write it like that here. P implies boom. Okay, so with this line, I suppose the left part, I got it, and my goal became the right part, which is this. I cannot try it today. Does that make sense? Okay, so now I look at it and I say, okay, kind of better than before, but the only thing I can do here is what? Like, I cannot attack the goal exactly because boom has no commands that attack it. It's not attackable, okay? It's not unprovable unless you explode the world. P, I know nothing about P, I cannot use it. This thing, I know something about it, so I can like fool myself that maybe I can do something better. Something like write an extra line. What's the only way I can use this? Yes, is it Michalis? No. What's your name? Stelios, sorry, Stelios.
Apply P. Unfold and apply P.
Okay, I'm doing all these unfoldings like in blue, kind of automatically. So let's do it orally.
I can't actually apply it, but the best I could do would be to apply it.
So this is the idea. So I would say I'll try to get the left-hand part.
Yeah.
So I will do claim, and now I'm getting suspicious. Because my only hope is to say claim the left-hand part, and I open a further sub-proof here. But if I see what happens, okay, let's see, what is my goal here? What is my state? I'm claiming this, so it means that my goal is to prove what I'm claiming, and I have everything that I had. So what's the next line here? The same that I already said, because we have an implication, so I know, I'm happy, supposedly. I'm very optimistic. I can suppose the left-hand side, suppose P. And now what happens is my state is not P, P, another P, and boom. And I need to prove boom. So at this point, I realize that the only way that seems to be possible to move forward will never end, because I don't get anything. Because this having 2 times, there are logics where this makes difference. Especially in linear logic, you can only use your theorems once, your hypothesis once. So in certain other logics, we're not doing this here. This could be provable while the other thing would not. But what we're doing here doesn't take into account how many times do we know that a hypothesis. So if the only progress we made was to go from this thing to this thing, we gained only a given. We already had the same given here. It's about time we gave up, okay? This is not a full meta proof that you cannot find a different, more intelligent proof or something like that, but for the time being, I want to get you to spot these things and say, okay, maybe I cannot do it. Yes, Lazarus?
Within the system of logic we have defined, can we actually derive a proof that this is not provable?
Not within the system for this thing, I think. For this particular proposition, you mean? maybe we can cheat and we can do it. I mean, we will see a way to do it, and maybe we can manage to translate it inside the system. There might be a catch. That's a good question. Definitely, our system will not be able to refute it. I know that this is not what you're asking. I'm leaning towards no, but we will come back to this question. Remember, ask it again once we have confirmed that, look, this is not provable here. Okay, so I want to see now what happens. Okay, any questions about us? Yes, Arati, sorry.
Δεν καταλαβαίνω, γιατί όταν κάνουμε apply στο τέλος.
This thing here?
Ναι.
Technically, we never did that, right? Because we never got out of this. So we haven't proved it. It was our desperate plan that eventually we would be able to...
Ενώ πώς το έχουμε το πέρα.
Where is this? Good. I'm sorry. Okay, it's a typo. Thank you. It's a not P. Thank you. So it's a not P, and how do we have this not P? It's because we supposedly have managed to prove our claim here, right? Okay, so thank you. And it's actually, there are two objections. First of all, where did we find P? And second of all, it would not be even applicable. You cannot apply this on P. This is only applies to the left-hand side of it, which is a not P. Okay, thank you. I'm glad that we're following. Big conclusion. It's not fair to say that not P and P are like interchangeable and equivalent. Kinda humorous, kinda social or human way to see this is that you think of the love of your life, and one day they tell you, I love you, and you're happy. And in a different universe, they tell you, it is not the case that I do not love you. And you definitely know that things are not going to go well from this point. So you already appreciate that this is a weaker statement than the direct affirmation of P, okay? Keep that in mind. Okay, so coming back, actually let's give it a name. I think it's a good idea to tell you the name of this. Propositions that happen to have this property, that their double negation is equivalent to themselves, are called stable. So I will define this because I will need to use it sometimes. So a proposition like, say, A is stable. And since one direction is always the same, the important part is the cancellation of the double negation, let's say. But I will state it like that. Is stable if the double negation of A is equivalent to A. If you prefer to write it like this, I will not make a distinction right now. So this is what stable means. So we just observed that it's not fair to say that all propositions are stable. That's what this means. Okay, so now let's move to the law of excluded middle. I have written something about it somewhere. Okay. So let's say that I want to prove, this will be much faster. Let's say that I want to prove that P or not P. What would my only hope be here? It's not an implication, so, and I don't have any givens, right? So I need to choose left or right. What gives me more chances? Like I'm looking at the left part and the right hand side, like where would you go? I mean, nothing will work, but let's say you want to fool yourself for a little bit longer. Yes, Manolis?
I'm going to not P because just P is...
You cannot attack it, right? At least if you go on the right, it's an implication and you have like one more step to fool yourself. So we'll go right. And if you go right, it means now that you have the same thing you used to have, nothing, but you're saying that you'll be able to prove not P, and now you say suppose P, And now, supposedly from this P, you are able to derive boom. And now, like a meta way to realize that there's nothing you can do is say, okay, if I was able to prove this thing, like from knowing nothing about a certain proposition, explode the world, then the whole system would collapse. I would be able to pick my favorite proposition, infer boom, use boom to explode everything, and I could prove anything. So probably this should not be provable. But this is just a meta kind of intuition. Yes?
Αντί για αυτό που κάνουμε, θα μπορούσαμε να κάνουμε left και suppose P πάλι.
No, because if you go left here, what's your state? Let's see an alternative approach here, okay? I'm going left, which means I have no givens,
Ναι, και έχουμε τώρα το P.
and I have to prove P. And now, if you say suppose something, I will tell you I'm not willing to suppose anything because I'm not forced to do that, because on your goal there is no implication. Remember, you are only allowed to suppose stuff that on the left-hand side and on an implication, right? This is why I argue against the advice that a lot of mathematicians give. You cannot ask as a given for the thing you are trying to prove. It's way worse than that. You can only ask for givens if you have an implication, and even in this case, you can only ask for this particular given, nothing else. Okay. Okay. So we've seen both ways. They are pretty doomed. Okay. And so let's give up. Okay. It makes sense. But we will prove. So there is a misconception starting from Hilbert and all this ugly story, that what we're doing here is incompatible with mathematics, that it kind of goes against everything that has been built and all that stuff, which is not the case. And we are about to prove right now that actually we are proving that you cannot negate this for any p. Sometimes this is called the irrefutability of Lem, of the law of exploding middle. I don't like much this name, but just letting you know what it's called, and I will tell you why I don't like this name, but it's okay for now. I don't need a name. I will just prove this. So technically what I'm saying, within my system, I will prove that this thing, with one negation here, is impossible. I will prove that it's not valid, okay? So let's see how this proof goes. Ideas for the first line should be automatic. Now we have more here. 5, somebody, please. Yes, Sarati, go on, please.
Suppose not P,
Go on.
P, E.
Very, very nice. Okay, P, all these things. The only thing that you are technically allowed to suppose. And maybe now it's a good time to say, all these things that you're forcing me to write here is actually a bit, pretty much just a comment, because since I'm only allowed to use suppose when I have an implication, and the only thing I can suppose is the left-hand part of the implication, maybe the command should be just suppose, right? And it will end up being, okay? But I think it's much nicer to read it like that. It keeps us in track, and you get a check from your system that what you think you are supposing is exactly the thing you are supposed to suppose. Okay, so what's my goal here? What's my state? The whole state, like givens and goals? Yes, Manolis?
The given is what you have next to the suppose,
Okay.
and the goal is bottom.
And the goal is?
Bottom.
Bottom, yes, boom, whatever. Okay. Okay. Now what do? I have no way. Anytime I want to prove something, every time I look at the thing I'm trying to kill and I see if I have any ways to damage it, to attack it. I don't have this because it's a bottom. And the only thing I can do left to do now is look if I can use my givens. Not necessarily in this order. It doesn't mean that if you know a way to attack the goal, you should do it. We've seen an example where this did not work. We had to use first our givens and then go back to attacking the goal. So, but now my goal is unattackable by direct means, and it should be because it's like a falsum. So the only hope is I can manage to find a way to prove, to use something I have. Ideas? Yes, Stelios. Am I right? Stereo, sorry. It sounds a bit the same. Sorry. Say it.
Claim P or not.
Yes, my only hope is to manage in my givens the only thing that makes this machine work. Like this machine transforms these kind of things into booms. So this would be nice to make it. Claim, and maybe you think, okay, he's running around circles again, but I will surprise you. Okay, so claim, my point right now is that it's not always that the optimist is wrong. So this we'll manage to prove this. That's the idea. So I'm claiming this. So what happens here, Asterios? What is my state?
I have as givens not P or not P.
Exactly the same things that I had, right?
Yeah.
Okay.
And my goal is P or not P.
My goal is the thing that I'm claiming that I will prove right now, obviously. And this is a subproof here. And what do you want to do now? Do you want to see if I can do it? Or do you want to see why, if I make it, I'm done? Okay, let's skip to the end. Let's skip to the end and say that I'm done. I think it should be pretty obvious how I go on from there. If I manage to claim this.
We apply not P or not P to P or not P.
Exactly. So here, if I manage to get out of this thing, what would my state be? My state would be you have not P or not P, which you already had. You also gain the right to this one because you just proved it. And from these two, you can have a contradiction. I will start using my abbreviation. And you are done. Okay, but we had reached a similar spot previously, so we are not so happy yet. Let's see, what can I do now? You might, just give me like a second, you might be fooled to think that we have already pretty much given up on the chances of proving this thing, and it seems that I want to prove the same thing, but it's important to realize that the games are not the same, because in this game I have something extra, right? While here I had nothing. So this is not a reason to give up. Even if you have realized that there's no way to prove this, you might be suspicious, but this is the most you have the right to be. Ideas. I only have, I will ask you, I will not give a hint right now, just say something. On my givens, I only have an implication, and if I try to use it, the only way to use it is to obtain this thing, but it doesn't seem very reasonable to open the same claim inside the same claim, because nothing changed, right? It's like I'm claiming this, I'm claiming this, and I'm claiming this, okay. On the other hand side, I have a goal. Maybe I can attack this. Who wants to give a suggestion? Like 1, 2, 3, 4, no, 3.5, maybe. Asterios, go ahead.
We can split cases on P or not P.
No, wait. When we say I'm splitting cases on a disjunction, it means that I have this disjunction. So if you have A or B, so you don't have a disjunction that you can use to split in cases, to separate in cases. It's pretty much synonymous. I will use separate for cases and split for when you're attacking a. So
now we say split.
You cannot say split because it's not a conjunction. It's a disjunction. So the split would be like if you want to prove a conjunction, A and B, you have to do two proofs. So you split it, I will prove A and I will prove B. Here is a disjunction you're trying to prove.
Either of those.
Yeah, you have to make a choice. You cannot say I will prove first the left and first the right. Nobody asked you to, right? First of all. So if you manage to prove the left, you say, I chose left and I'm done. So if it was a conjunction, you have to prove both parts. You split it in two and you must finish both things. But now that you are trying to prove a disjunction, you pick a side and you stick with it and that's it. Okay? So you need to make a choice, and this is the difficult part. Usually the most difficult things is when you need to find a witness to prove an existential or to make a choice, left or right, in a disjunction. And a lot of times you want to wait until you elaborate more on your givens, but now we cannot elaborate on our givens, so it is the time to choose. So we have to make a choice, left or right. Where would you go? Now, who would go left here? Who would go right? Okay, and then indecisive a bit. Let's go right. I mean, why? The reasoning is like how Manolis argued. If you go left, you just gain, your goal is not further attackable, it's just a P, you know nothing about P. It could be an implication, but you don't know it, okay? So you cannot attack it. If you go on the right, at least you can attack it a bit more. So you say, it's good, I will gain something. So let's go right. So what happens here is that this thing, we've went right. What changes in my givens? Somebody? With this command, I went right. Nothing changes. Okay, that's the. I will ask these kind of questions. Okay, we need to know that, right? Okay, so what's my next line? Kind of obvious line. Yes, Arati? Yes. This is the whole reason we chose to go right, because we can do further stuff. Okay, and now what happens here is that. Like something like that. Does that make sense? Okay. Kinda hopeful that maybe this will lead somewhere. Let's see if it will. What do I do now? Maybe this is the second time that it feels like I will not manage to do something, but Asterios has a different, is an optimist and is good here, yes?
Yeah, I wanted to ask that and
okay.
but
You should have, okay.
Can we just say like since I have P, I can get P or not P?
Okay, very good question. So let's do that. And we'll not get away with it for free. We should make sure that what we already have allows us to do it. Otherwise, we have to say we need to expand our language of proofs and our system to include this kind of reasoning as well. So the idea is that we don't have to do it, but it's quite convenient to say something like, therefore, or hence, P or anything I want here, right? I have P. Therefore, I should be able to derive the disjunction of P with anything. And what do you want to put there?
Do another subgroup like claim P or not P.
Yeah, exactly. Okay, so the short way, like the intuitive way, would be, what would you choose here? Obviously,
Not P.
Not P. And now that you have P or not P, you can be careful. This contradiction here is within this thing, right? Contradiction, and now this contradiction that I wrote finishes this claim here. So this is done, and this is done. Okay, so the only fishy thing for the time being is, can we really do that, the yellow thing? And yes, we can, because we can substitute the whole yellow thing with this yellow thing. So I think Asterios already saw how he can do it. What was the idea?
Another subgroup.
Another subproof, exactly. So here, I would say, let's try to do it like that. Okay, this would be like claim. What will you claim here? Yes? P or not P. And, like, technically like 2 or 3 minutes ago, I said it doesn't make sense to reclaim the same thing that I'm claiming. But this was when it was just the first line, because it had the same state. Now I'm claiming this under different circumstances. Okay, so it makes sense to investigate. So I'm claiming this, and how will I prove it? Where will I go now? It would be a mistake to say every time I have a disjunction between something and negation, go to the negation because it will give you something. Yes, Konstantinos? Yes. Okay. So here I'll go left this time. Probably apply something like apply. Help me here. What on what? Apply. It's immediate. Yes. Okay. So it's exactly P. Okay. So. everything finishes off. And this is like maybe the first proof that I told you that you are able to follow line by line, but it takes a bit to realize what's going on. And that's normal. And yes, it's time, according to this clock, it's time for a break. 2 minutes ago. And according to that one, I have a few more minutes and I will trust this one for the break and this one for when we go back to our class. So we have like 2 minutes extra. Yes, tell me.
Στο claim χρειάζεται το contradiction. Όχι αυτό το αρχικό claim.
The outer claim?
Μετά το hence.
This one?
Ναι, εφόσον έχουμε το P or not P που...
No, you're right. No, sorry, you're right. This contradiction seems useless here, right? Because I have derived this. Okay, it's not a contradiction here. It's I mean, okay, it works. Okay, let's see that. Good question. I could do contradiction here. Why? Because on my givens I have this, and I have this as well. So it works.
Yeah.
And then you say there's a different way to finish this proof, and you're absolutely right. Okay. Which what exactly? It's exact. I already managed the thing I wanted to prove in my givens. Other questions? We have managed to prove that it is definitely the case, whatever proposition you are looking at, there is no way you will negate this thing. Okay? So the reason I don't like the idea of irrefutability of Lem is that, okay, I will finish with this for the break. Technically, the irrefutability of Lem would be this. It's not the case that it's not the case that Lem. But inside Lem, there is like this for each P, P or not P. But what we have proven is like for each P, it's the Lem for this P, like, okay, is irrefutable. Does this difference make sense? Because if I wanted to negate this, technically, the for all should have become an existential here. I'm not saying I have not proven that Lem is irrefutable. I have proven that for each P, this thing is irrefutable. Lem is the big law that says that all propositions are, okay, definition, fancy word, where was the stable? So we call it proposition decidable. And after this, we have a break. Means, I don't know why I did that, okay. Means I can prove A or not A. And maybe I want to say that it's decidable within a certain context with some givens. In this case, I would say, okay, it's gamma, it's decidable in gamma or gamma decidable if from this context I can prove it. Okay? So let's take a break and let's come back in 10 minutes. Is that okay? I hope it is. I'll end the recording here. Okay, so the thing I would like to do now, if there are no further questions about what just happened, which is okay if you have like if it seems a bit weird, I would like to pretend that we are trying to prove something, and the whole point here is I want to convince you that there is no. The thing we're doing here, the kind of mathematics we're developing here, it's not like a different religious or whatever, a cult of weird stuff, because some person thought, let's, from the list of all tautologies, let's see what happens if we don't accept this, and something like that, investigate. So it's reasonable to say, like, why this one turns out to be kind of problematic, and I would like to see and remind you how we use these junctions in order to argue that what we end up doing is not incompatible with like what Hilbert is doing. It's just a way to see clearer some distinctions the feeling is like you put on your glasses. And you realize that you were missing a lot of things, a lot of stuff that ended up being equivalent. You start noticing things and you start paying attention and you say, please, for the rest of the world who they're not using your glasses, let's be careful of what we're saying, because otherwise we're losing these details when they matter. Okay, so let's say I'm trying to prove something about number theory, and I have some hypothesis like, I don't know, maybe n is, let's say I have a prime p. So first of all, okay, I have an integer p, and I know that p is prime, and I know a bunch of other stuff as well, and I'm trying to prove something, I don't know, a goal g, it doesn't matter. And I'm doing stuff, I'm writing my proof, and let's say that, yeah, I'm at a certain point, and I say, since p is congruent to 1 modulo 4, let k such that what am I trying to do here? Like p equals 4k plus 1. And then I go on with my proof, and eventually I claim I proved it. Now, everybody should object to this line. It's kind of I'm lying in the same way that like lots of politicians lie, saying like, okay, since we have advances there, we can do that. But you only get to say that you have advances there if we already know that we have advances there. Here I'm like pulling up my sleeve a random thing that I don't have in my data. Okay, we may think it was there. Okay, it's not. Sorry, I should have emphasized it. The idea is that here I don't have this information. Okay, so out of nowhere in my proof, I'm trying to use something that I don't have. Say, okay, since p is congruent to 1 modulo 4, it means that there exists, it means that 4 divides this thing or whatever, and therefore I know that p is of this form. And then I do further stuff and I prove it, but nobody should accept this because you should say, you're using here something that you don't have. This does not compile, as I'm saying in this course. You're cheating, the proof is wrong, 0 marks, or if it's an exam, I don't know. And maybe someone would say, okay, how about all the rest? Okay, but crucially, you're using this. So, no. Are we okay with what I'm saying? Do we agree that this is like cheating? No, Konstantinos?
Προφανώς θεωρούμε ότι δεν μπήκε σαν κείμενο.
Yeah, thank you. This is an important thing. Okay, so let's say that at this point, my state is this, and it doesn't have like, okay, let's say it doesn't have anything else, okay? Because you are right, maybe I have done some work here, and with the extra stuff here, I have managed to infer this. Okay, but let's say I'm pulling it up my sleeve, okay? So, you should say this line does not work, therefore the proof does not work. And now, but let's say that it's a beautiful proof, besides this subtle point. If you ignore this, the proof compiles and you manage to get G. What is a reasonable thing to do for the person who spent like 3 years on this proof? Kill themselves, it has happened, probably, but what's the yes, Manolis? Yes, say, okay, okay, you're right, I don't want to lose my proof. I'll just be a bit honest here, and I'll say I have an extra thing, which is what? Which is that P is congruent to 1 modulo 4. And now I don't even have to review my proof. The whole thing compiles, it's perfect. I've proven something. So it's like my proof was valid for a certain game, but it was not the game I was claiming to be playing. Okay? So I say, give me this, and then the whole thing works. And now, if I still want to prove the original thing, I have to do a different proof. I have to look for it. Okay? Does that make sense? Okay. Now, if we remember what ERRATA did, I think, on Zulip, trying to prove something, eventually, she said, okay, K is, I don't remember what it was, A. I will do this. And then K is not A. I will do that. Now, if you see this in a proof, you should have the same irritation with this kind of thing, exactly the same one that you had here, because here you are using something you don't have, which is, I don't know, this thing. And here you are using something you don't have, which is the given you would like to have in order to use this. Arati?
A or not A.
Exactly. This is a use. This is how we use these junctions. This is a use of A or not A. So if you have this on your proof, you better know this, right? A or not A. So let's say Hilbert has written a proof and has a bunch of these things there. You can be like more honest, saying, okay, you haven't proven this, what you thought you were proving, what you are claiming you're proving, but your proof is okay, just add here A or not A. And maybe within here, or maybe outside at some other point in your proof, can be a big proof, you also split on a different proposition and its negation. So add this thing there as well. So your proof is still valid. It's you're proving something. The only thing we are doing is like we are being honest of what is being actually proven. And in case you take off your glasses and like you become Hilbert in the sense, you say that nothing changed because this thing is redundant because it's valid for any proposition, this thing as well. You still think you have proven what you thought you had proven. So there's no way to like quarrel about it in this sense. Just a second. A much more atomic explosion kind of thing, brutal bazooka, name it how you like it, is say, instead of doing this, say, for this theorem, I will also claim that I have lem. What is lem? Lem is like an oracle, and this is why I emphasize, we say that this mathematics we're doing here is as if humans matter. It's like a divine oracle that you give it any proposition you like, any p, and it gives you back the disjunction. So how you invoke, you would say, okay, give me lem on p, and what this would do, you gain p or not p. It's like you have an access to this oracle, and it will tell you for any proposition if you go left to prove it or you go right. Obviously, this thing cannot exist in our human nature, but like when you're seeing things classically, the way Hilbert would advocate here, it's like as if you have an access to that. Okay, from the computational constructive point of view, it's completely meaningless. It's as if you're writing a computer program and you say like, if, I don't know, the Goldbach conjecture is valid, print hello, otherwise print bye, and you don't have the obligation to say how to resolve this part here. Anytime you split in like two cases, remember we are seeing these proofs as a sequence of instructions, and you are telling me do this, do that, take the compass, I don't know, suppose this, and I'm at this point following your instruction, I have reached this point, and now you tell me in case A, go here and do this stuff, in case not A, go here and do this stuff. But you haven't told me how to decide this question. It's maybe not so simple to decide it. So the point is, if you go through like Euclid or something like this, you will see a bunch of case splitting between something and its negation. And Hilbert will say, you want to collapse everything, we are losing everything. Actually, no, because Euclid took the time to tell you how to decide things. So like, for example, anytime in number theory, you would see something like, it looks like a use of lem, but it isn't. Okay, this is what my big point here. You would say something like case n is even, or case is not even. Or maybe you say things like case P is of that form. I will write it in quotes, like for K plus 1. Case it isn't, or maybe you see something like case P prime. I don't like this example, forget it, sorry. Okay, and case P is not prime. And all these things to the untrained or to the brainwashed mind, whatever, seem things that a constructivist would not be able to do. But it's just that you have the obligation that when you're splitting on this, first of all, tell me how, given any integer, how can I decide if it's prime or not prime? And Euclid does that. Tell me how to decide if it's even or not even. Divide it, see the remainder. If it's 0, it's even. If it's not 0, it's not even. So you know how to proceed. So it looks like you're using, you could use lem, but it's like, instead of asking Euclid and taking the algorithm that decides whether it's prime or not, you prefer to ask God for the holy wisdom of is P prime or not? And if your oracle says yes, do this, or your oracle says no, do that. Okay, so I think Asterios said something similar. Maybe, I'm not sure who said that in Zulik. Like a lot of times it looks like, oh, this is not constructive, but actually it is, because you have a way to decide all those decisions that you are saying. So pretty much Euclid proves that in our terminology that primeness is a decidable proposition. Like factorize it, and I will tell you how to factorize it, see what the factors are, and you know if it's prime or not. So you know how to decide this. You can decide evenness of the parity of an integer. Divided by 2, you get it. You can decide here when you want to split in 4 cases, 4k plus 0, plus 1, plus 2, plus 3, you know how to do it. It's the Euclidean division. Do it, see the remainder, you know in which branch to enter. So just a big alert, because a lot of times we think that, okay, you cannot do that, okay, because you are being constructive and now you're using lem. I'm not using lem, because I have established that this particular thing is decidable. And if I have not established this, I could add it as an hypothesis on the statement of what I'm trying to prove. But instead of being brutal and say, I will use lem, I will see which case splittings I needed. So here in my example, I needed A and B, and I say, supposing also that A is decidable and B is decidable and a bunch of things, I will prove my thing. And maybe later on, somebody will come with a proof that doesn't need the decidability of B, or maybe eventually I will be able to prove that B is decidable, and then I say, okay, I don't even need it because I've proved it. Okay. I'll sip some coffee. Questions?
Δεν είναι τόσο αυτό που στο point, αλλά γιατί χρησιμοποιούμε case όταν έχουμε διάζευση.
The only way, the way to use a disjunction is exactly this. You split it by cases. Because what does it mean to know a disjunction? I'm certain about A or B. In this metaphor, I know it's a bit childish and silly metaphor, okay, but I think it works well in this monster killing business, and you have your weapons, right? Okay, you can think of disjunction A or B as if it's like a box. First, let's say conjunction. It's a box, and you know that inside it there is a weapon of type A and a weapon of type B. You know that. So eventually you can open it, extract the left part, extract the right part, you have these weapons, A and B. The disjunction is like a box. It's written that inside it, you will either, on the left part, you will open it, and you will either find something of A, which is the left possibility, or you will find something of type B, which is the right possibility. So imagine like a box that only has one hole. You don't know yet if it will be on the left or on the right, and inside you know what you will find if it's on the left or on the right. So when you give instruction of how you will checkmate, how you will kill the monster or whatever, you have to tell your guy, opening the box, in case you find the left-hand part, do that. But you cannot be done with this, because the player, you say, okay, what happens if I get the other thing inside? It's like a box, you know something about it, but it's not a concrete information. It's either left A or left B, so you need to provide 2 proofs for both possibilities. In case it's an A, do these things. In case it's a B, do that. And when you're at this point, you have this thing, you have the disjunction, so use it, open it, and you know if you go left or right. Right? If you don't have it, you use lem to gain it, and then you use it. Okay.
Απλά, τώρα ούτε το κάνουμε attack, ούτε το χρησιμοποιούμε. Γιατί,
The disjunction?
ναι,
We are using, in this point, you are using a disjunction. The question is, where did you find it? If you already have it, perfect. You have it on your givens, you use it. Okay, if you don't have it and you have access to this divine oracle, you say, I'm using this. You use this command, like I'm invoking lem. On P, you choose which proposition you want to get the magic box, okay? And then you gain on your givens P or not P. And now you use it. You say, I split on the case, the left case and the right case. I separate on these cases. Am I answering your question? No. Okay.
Ωραία, καταρχάς όλα αυτά είναι μια απόδειξη. Σωστά.
Ναι, all this is supposed to be like a proof.
Ωραία. Στο πίνακα με,
Okay, the givens goals.
με τις προσεγγίσεις, για το π.χ. για τη σύνδεση, για τη διάζευση κτλ.
Okay.
Για τη διάζευση έχουμε ότι για το κάνουμε attack αποφασίζουμε τι θα πάμε
Exactly.
και για να το χρησιμοποιήσουμε
We split.
παίρνουμε τη μία από τις δύο.
Okay, no. So this is the whole point. If you want to take advantage of this junction, it means that even your enemy has agreed that A or B. You don't know which, right? So you don't have the right to say I'll go left, because the only formation is ambiguous. You know A on the left, that you will find an A on the left part, or you will find a B on the right part. You don't get the right to say I will substitute this box with the left part, right? This is the whole point of this junction. You have to take into account both cases.
Δεν διαφωνώ, απλά επίσης σε προηγούμενη απόδειξη τώρα.
Did we do something silly? Maybe, I don't know.
Αυτό και
Which one?
δεν θυμάμαι.
If at some point we use the disjunction selecting which of the things we want, that's a mistake. I don't think we made this mistake. Maybe you are confused about this thing. Okay. So if there's something, you bring it to Zulipen. But I hope it makes sense. A or B is a weaker statement than A, and it's a weaker statement than B. So I should not be allowed to say, I prefer A, right? There is a duality when we put these things on the proof-theoretic and logical terms to investigate all these connectives. This duality will be very clear. Like if you see what happens here on this table, there are certain similarities and certain dualities here. I have two ways to use conjunction, and this pretty much means I have like two ways to attack disjunction. There is only one way to attack conjunction, and it splits the thing into two. There is one way to attack, to use disjunction, and it splits again the game in two games. Okay, so there's like some connections. When we put this on our table to discuss them more, we'll come back to this. Okay, so is everybody like kind of satisfied of this? I'm trying to get you to the point that when you see in any proof, and sorry for infecting you or liberating you, I don't know how you want to say it. Anytime you see case, I don't know, A or not A, say, okay, you're using some kind of magic here. And it's okay if you don't care about it, but I want to be honest, and I will say that my theorem depends on magic, or at this particular instance of decidability, that A is decidable. So we're just being a bit more honest, and if somebody doesn't care about it, we don't fight. I mean, there's plurality in what we're doing, okay? Is that understood? It's okay? Can I proceed? Okay, perfect. I haven't talked about equations, equality, so let's finally do that, which is the last thing that I want to talk about, not for the semester, obviously, but for logic. So what about equality? First observation, we've talked about this already. It's not one equality. For each type alpha, we get to write the symbol between two elements of the type, and we form a proposition. So the thing is how we use equality and how we prove it and what we assume valid about equality. And the first thing that should definitely, anything that deserves the name, is an equivalent relation. It means, I think all of you know that, but let's refresh our vocabulary. It means that it has two properties. It is reflexive. It is transitive. And it is symmetric. This will be a crucial question. Because for the time being, I cannot say I will prove them because I don't even know what this means. Pretty much I'm saying whatever this ends up meaning, it definitely should have these properties. Maybe we'll manage to say these are, let's say, primitive, and we manage to prove the others. So it's an equivalent relation. I will introduce a syntax now, which we will be using all the time. For some of you, it will be new, and it's extremely convenient. It's like rules of inference. You can consider it for the time being just as some convenient way inference. They look like fractions, but have nothing to do with that. The idea is, I write here a bunch of assumptions or prepositions or premises. I draw a line under them, and I say from these things, when I read it top down, from going downwards, from these things I can infer this thing. Se, just to remind me that it's a conclusion. I'm using the letters J here because all these things are judgments, usually. But sometimes I will abuse the notation that will be propositions as well, judgments. And the idea is that from these things, how many things have I written here? What's the convention? I've written n things. And n usually denotes natural numbers, which include 0, which means that here I have 0 or more premises. Oops, sorry. I have 0 or more premises here, and I'm concluding how many things have I written below that? Exactly 1. So this is how we will always write this. This is my conclusion. These are the premises. This is my conclusion. It will be extremely handy to have access to this notation. And here I usually want to give something like a label. Let's call it, I don't know, L. This is the label, like the name of the rule I'm using, let's say. So I will present this just to get used to it. I will present this as inference rules for reflexivity. What does reflexivity means for equality? Somebody? Yes, Konstantinos?
Alpha is on alpha.
Yes, it's like for any A, right? What is it? For any A is equal to A. And I will summarize this like that. Out of nowhere, I know that A is equal of to A, and the label of this thing is refl for reflexivity, or just an R if you are lazy. But what I'm saying is, out of nowhere, I don't need anything, I can infer this. Maybe you don't like the fact that, I mean, like, what is A? It's like it came out of nowhere. We'll fix this later on, but the idea is like it's some A, okay, of some type alpha, and I'm using here, so there's an invisible alpha here, and the idea is that A has the correct type, okay? So for transitivity, how can I write it in the same notation? Now it will be kind of more interesting maybe, because I will have as premises that A is equal to B, and also that B is equal to C. And from these I can infer that A is equal to C. So this will be like, the label for this will be transitivity, trans for transitivity. And can somebody guess how I will write the fact that it's symmetric in this notation? Lazarus? Exactly. Okay, so it's only one premise. From A equals B, I can deduce, I can infer B equals A. So, since I'm explaining this kind of notation, it's important to appreciate both ways of reading this. If you read it this direction, it means if I have all of these, I get the right to infer this. Think of it not only as premises, and not as a conclusion, but maybe a construction you are doing of some kind. I don't know. These things will end up being synonymous sometimes. Construction. And this is like maybe, I don't know, the ingredients that you have. The data, the information, I don't know how you want to call it. So if I read it top down, I'm saying that having all those things, I can infer this thing. If I read it bottom up, if I want this thing, it is sufficient to help me with the word, to get my hands on those things. So it's like I'm reducing the problem of solving this thing, of constructing this thing, of proving this thing. I can reduce this to this 1, 2, n new problems. So if I like to focus on my goal, it's like I'm on the route. This will be my final goal, and I keep going up because now maybe I don't have this, and I have to justify it furthermore with further promises, and these further promises, and so on and so forth. Does that make sense? We'll see, because so far we have only seen like level 1, like if you see them as trees, their height is only like 1 or 2, or maybe 0 and 1, okay? But we see that these things can compose and have a structure. You've seen this exactly when you were in high school or in elementary school, not in this formulation, but when you start to learn what parentheses mean. So maybe you've seen something like this, a tree that grows down and goes something like that. I mean, this is when you're parsing this expression, your mind does something like that. So this syntax is very similar. One difference is that it doesn't grow down, it grows upwards. So let me write this thing, how we would write it with this syntax. It would be like, okay, 3 plus 5 times 2. Like I'm using probably some kind of formation for multiplication. This would be like 3 plus 5 here, and 2 here. And, okay. 2, let's say that I already know that it's a number, so I'm done with it. But 3 plus 5, I need to justify it further. It depends on some formation using the plus here. And now I know already for some reason that 3 is an integer and 5 is an integer. And this kind of thing that I wrote here is how we would write the tree that maybe you've seen before. So one difference that grows upwards and downwards, you can argue that this is a silly difference. But the other thing is that actually I have visual access in every intermediate construction. This is supposed to represent the sum of 3 and 5. I don't see it right here, while here I actually see it, okay? And we will enrich this notation. So, are we okay with the part that equality should be an equivalence relation? I hope so. But equality is way more than equivalence relation. It's like the best or the worst, depends on your point of view, of the equivalence relations, because it's like required to play well with any context that something appears. The idea is you can substitute equals for equals in any context that you are, whether you want to substitute something on your goal or on your givens. If you know A equals B, and we will come to the main usage of A equals B, if you know A equals B, what right do you have that you didn't have, you wouldn't have if you didn't have this on your given? Sorry, I messed up my phrase. You get the right to substitute A's for B's anywhere you like, okay? So, this is the most important thing of equality is substitution. And I will not write this in a good way, but pretty much let's come up with some notation. We will fix it later on. If A is equal B, and maybe I will want this for future reference. Okay, forget about this now. So if I know A is equal B, and I have some expression, anything, I will call it like T of A, where A's appear, I get the right to substitute it with, substitute 0 or more occurrences of A by B. So for example, maybe I know that A squared plus B plus C is equal to D plus A. I can infer by using this equality, A equals B. I can infer that, okay, pick your favorite A, or both of them 1, and substitute with B. So I can infer that B squared plus B plus C is equal to D plus. If I want to choose this A as well, I can put a bit here. If I don't want to, I can leave this as A. This is the use of equality, essentially. Would anyone object, like logically, that if some things are equal, we should be able to substitute equals for equals? I mean, this is what equality pretty much is. And the question is how we attack it. So for the time being, as an attack for if I have an equation to prove, look, all these things are my conclusions here. So if I have A equals B, I have like 3 options to pick from. And furthermore, as we have established, some types might give me further things. Like for sets, it's enough to prove that A is a subset of B and B is a subset of C. So each type might give me further axioms, further things I can use. But I want to argue now, like a simple exercise, that I do not need these. I definitely want this, but this should not be primitive. So let's try to prove, let's try to prove one of them. Okay, let's try to prove this, maybe. Or I could leave these as exercises and do a more interesting one. Okay, we'll see. But what should I do? Okay, let's do some group theory. Okay, you all know what a group is? Everybody, indeed? Group. You see groups in, maybe not. Monoid? Maybe a bit. Okay, let's say, okay, I will not define a group now, although we might do it by the end of the class. I'm trying to prove that in a group, okay, inverses are unique. So I have A, which is an element of my group. And I want to say that there is only one element in group that satisfies that A times U or I don't know, is equal to, think of this as 1, okay? I can write 1 actually. Okay. And think of this as multiplication. So how would a proof like that goes? You want to prove uniqueness, you proceed like this. You say, suppose there are 2 guys satisfying what I want, and I want to prove that they are equal. So how would you do that? You say, like, suppose that I have I and J, and they are both deserve the name I am an inverse of A. Okay? And I want to prove, my goal is to prove that I is equal to J. Is that a good proof? Let me think about that. No, a simple one would be the cancellation property. Sorry about that. You can even think of numbers if you don't like groups, but like, let's do groups. I want to prove, sorry for the mess, I want to prove that if I have CA equals to CB, I can, this implies A equals B. This is the cancellation law for groups. Essentially, it allows me to cancel the C's. Okay. Whoever has seen the definition of a group definitely has seen this as an exercise. You are allowed to cancel things on a group. Who hasn't seen groups probably reminds them of numbers. The only detail is that you cannot cancel if you have 0 there, but we're on a different setting. So how would this proof go? There is a ugly proof that you may see in group theory. I want to prove this equation, so I know a way to do it. I will say compute. I will put one at the left-hand side, let's say, on the table, and I'll start computing. And I hope that eventually I will reach B. What would the first step be here? Can anybody see it? Manolis has done group theory, seen some group theory. A is equal to?
1 times A.
Yeah. So this is like a weird inspiration. Because you are, usually when you're computing, you are simplifying things. Now you start from A and you are inventing something, 1, and say, okay, this is equal to that. And we can say it's not such a big inspiration. It's like a divine thing. Okay, 1 times A. It's kind of weird because you're complicating the thing. And then you need a much further inspiration, which would be which one?
C to the minus 1 times C times A.
I think you will need this, actually. You said the other way around. You might be right. We'll find out right now. And this list is like, we'll see. If this, oh no, you're right. Sorry. Yeah. Okay. So at this point, out of all the infinite things, this is way more bigger inspiration. Manuel said, I will substitute 1 for this product, sum inverse times itself. And you could put anything here, have infinite options. It's kind of obvious that it's C minus 1, C that you have to put here. So what do you do next? C minus 1, C A, I'm doing this very fast. And now finally you use that they are equal, and you write like something like CB, and now you use associativity, and now you're back to 1 times B, and now you are B, and you say, I proved this equality. If you've seen proofs like that, maybe you're used to them and they don't seem ugly. It's really ugly. It's okay. Nobody would doubt that it's correct, but it's okay. Let's compare it to a different one. You'll get what I mean. If you liked it, I hope that you will not like it by the next or the following minute. I can say.
Is more common.
What?
I think the other version, which is what we're probably about to do, is more common.
That's a good reason. Okay. So it's more. If you want maybe for your students to say, aha, he's very smart, he came up with all these things, they are correct, you can impress them. You shouldn't be impressed by this. It's quite the contrary. So the other proof is like saying, since CA equals CB, then, so I'm using this fancy word here, then C minus A, CA is equal to C minus CB. Hence, you do these things, and you may argue that it's the same thing. It's not. Because you can actually understand where all the inspirations came from here. Hence, 1A is equal to 1B, and hence A is equal to B. And actually, if you want to impress people who get impressed by silly things like this, and you have this, you can hide it, like you can go like this way. Does that make sense? You can say, aha, A is equal to that, equal to that, equal to that, blah, 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 and I managed to do it in a direct way. There is absolutely no merit in proving this thing here or there. But each line, each verb on your proof requires a justification. So orally, I don't want to write this down, we don't have the time. How do I justify this line? Remember, justifications justify pretty much the verb of the line, so you need to tell me why these things are equal. This with that. And then why this with that, and all those things. So let's go. First line, what's the justification of this one? Yes?
The definition of identity.
Yes, it's the identity of the group. Like, okay, then is the definition of C minus 1, which if you multiply it, either on the left or the right of C, will get you this. Then you use the associativity. Then you finally use your data, your given, to substitute something with its equal, okay? And then you do these things backwards, right? Associativity again, inverse again, identity again, and you justified everything. So there is a subtle point, and I want to do this before we finish this class, because I think we will have a tiny bit of justification problem here. How do I justify this step? This hence here. That's easy. Good. It's two identities, right? I like the identity of the group. To substitute this for this, I'm doing two steps here actually. And this by this. Okay, so there are two steps here. Similarly here, it's two uses of inverse, and here it's two uses of associativity. Here and here. So I have like 6 or 7 steps here, which is pretty fair. How do I justify this one? What is the phrase that you will see everywhere, like in, when you're doing mathematics? What did I do from here to there? Somebody? Nobody objected, right? From this to that. So you should have a like why? Why can't? What am I? First of all, what am I doing here? And secondly, am I allowed to do this? At least with the system we have so far. Arati? No, it's not. We are multiplying, but not. No, wait. You started nicely. We are multiplying this equality, both sides of this equality, by the same thing. But that same thing is not say minus 1. What? Wait. That's the next question. Wait. First of all, what am I doing here? I don't doubt that this is the only way that this is usually written down. You multiply on the left-hand side, which is important because you are in a group in this case. If you don't know what a group is, ignore it. You are doing this. I will write it like that. This is you are multiplying by the left both sides of the equality. And somehow you get away with it. Because nobody will say, wait a minute, we've seen all these things, basic things, primitive things, we're allowed to do this, that. If we want to do that, we should add it to our axioms for equality. We should have the way, the ability or the right for any function that you might have. If you have u equals v, you should be able to infer f of u is equal f of v. This is function application. We'll talk about it in the next class, the notation. So do we need it as a law, or can we infer it by the things that we already have? This is the. Any of you two guys have a question, or is it a possible answer? Possible answer? Asterios, first of all, what do you think? We need it as a primitive, or can we prove it?
No, we can prove it by the fourth thing we said about equality, substitution. Yeah.
Not only. You will need something else. Let's try to prove it. How will we prove it?
In the place of p of alpha, we will have f of u.
Sorry?
No.
You want to you
also need reflexivity.
Exactly.
Yeah.
So you will need reflexivity to boot things off, to start things off. So what you will do is like
U equals f of u.
Say it again. Sorry.
F of u.
Exactly. So you say. F of u is equal to f of u. How do you justify that? That's just reflexivity.
Yeah.
You have u equals v. And how do you use that?
Substitution.
Substitution, yes. And we'll have to come up with some kind of notation because I want to say which occurrence of u I'm substituting, and let's say I will number them. So I'm substituting which occurrence of u you want to substitute by v?
Right.
The right one.
Doesn't matter.
It kind of does, because if you substitute the left, you will have to do the symmetry. Okay, so let's do the second one. I don't know if you like to start with 0 or 1, but now you get f of u is equal f of v. And this works for any f, right? So the crucial thing that a lot of times we do, we apply the same thing on both sides of an equation, It's not like a primitive law we need to do. Asterios just proved it just by substitution and reflexivity. So this is more interesting. This is why I chose to prove this. But like as homework, verify that you can prove this, these two as well from reflexivity and substitution. So on the next class, we will be done with functional notation and ideas. And I hope that from this point on, we will start investigating, like the introductory part finishes. I think we have some vocabulary to move around, and we'll start investigating all the theories that we need to end up having an actual proof system and start working with them as well.